Assalamu alaikum. Welcome to lecture number 16 of digital signal processing. So students, in the last week we have started our discussion with a new topic which was frequency analysis of signals. And under that topic we have discussed several techniques which can be utilized to analyze the presence of spectral components in any signal. We have started our discussion with the term analysis and synthesis, and we moved on to discuss the modeling technique of any signal with the help of sinusoids. Because we are dealing with the Fourier tool to analyze any signal, that's why we first see how we can analyze any real-time physical phenomena by the usage of mathematical expression which involves sine and cosine terms. So we saw there we can easily interpret any physical phenomena in terms of sinusoidal mathematical expression, which was also valid to estimate our signal and its frequency components on the basis of sine and cosine waves. Then we discussed several techniques which are available in literature to analyze any signal, and we also discussed the limitation of these techniques, which is these techniques can easily convert any signal into its frequency domain representation, or by using these techniques we can easily analyze the spectral components of any signal. But the limitation was that signal must be pre-recorded. That is, these techniques failed to realize or analyze any real-time signal. However, these techniques are equally valid to analyze any signal which is recorded earlier. And there, during that discussion, we have discussed these four techniques written on the slide, which are CTFS, CTFT, DTFS, and DTFT, to analyze any signal accordingly. We first look at the nature of the signal, which kind of signal is, and then we can apply the technique accordingly. Since we are dealing with digital signal processing, so we are more interested in those techniques which deal with discrete time signals, which are last two techniques, which are DTFS and DTFT. However, we can also analyze any continuous time signal with the help of these techniques, but we have to first convert that continuous time signal into discrete time signal by the process of analog to digital conversion, which we have studied earlier. So once the signal is converted into discrete time, we can apply any technique, DTFS or DTFT, depending upon the nature of the signal. If our signal is periodic in nature, then we have to apply discrete time Fourier series, and if our signal is aperiodic in nature, then we have to apply discrete time Fourier transform. So we will expand our discussion with these two techniques in much detail by taking some practical examples and application, by considering some arbitrary signals and try to find out its spectrum, which means which frequency components are present in that signal and how we can find these spectral components with the help of these techniques. Apart from that, we have learned some interesting relationship between time and frequency domain in the previous lecture, which are the relationship between lobe width and the pulse width of time and frequency domain respectively, and the spectral spacing and time period of any waveform. So we will apply these concept on real-time wave and we'll see how the change of one parameter affects the nature of other parameter. But we will limit our discussion to DTFS and DTFT, as I already mentioned that we are more concerned in digital signal processing, so we are more interested in discrete time signal processing techniques. In addition to this, we will try to learn which robust technique we can actually apply to realize any real-time signal. As I already mentioned that these techniques are paper pencil based, or these techniques can be employed on pre-recorded signal. So for any real-time signal, which technique we can use to analyze its spectrum? Starting our discussion with discrete time Fourier series. Now we have to prove that spectrum Ck is periodic by n samples, where n represent the time domain periodicity. That is, we have to prove this relationship as written on your slide, which is Ck is equal to Ck plus n. First, understand what this relationship states. Actually, Ck is representing the analysis part of DTFS. By the term analysis part, I mean to say the analysis equation. So analysis equation will give us the frequency domain representation of any signal, or we can say that if we have a time domain representation of any signal, we can apply analysis equation to get the frequency domain representation of that signal. And by the term frequency domain representation, I mean to say the knowledge of spectral components which may be present in that signal. So Ck is representing that, and the statement is saying that Ck is periodic after every n samples. Ck is frequency domain representation. Remember that Ck is a spectrum. So here it is saying that spectrum is periodic by n samples, where n represent the time domain periodicity. Here n is the time domain periodicity, which means that you have a signal in time domain and may be continuous, and you first convert that continuous into discrete time signal, and after converting into discrete time signal you will get samples. So after n samples your signal is periodic, because we are discussing which technique, DTFS. And remember the point that DTFS can be applied only to analyze those signals which are discrete in time plus periodic in nature. So discrete in time means these we have sequence or samples of that signal, and Fourier series is representing that we are going to analyze any periodic signals, means samples are periodic. So in time domain we have different samples, n number of samples, and the waveform or samples are repeating themselves after every n number. So this is the time domain discussion. And if we are going to take the spectrum, and we will opt the analysis equation of DTFS to obtain the frequency domain representation. So once we get the frequency domain representation, which means the spectrum of that signal, so we must see that this spectrum is also periodic by n samples, and n is not the frequency domain representation but the periodicity of time domain. So here we are going to prove this statement. So for proving this statement we have to consider the analysis equation of DTFS, and the analysis of equation of DTFS is written on your slide. So remember that this is the analysis equation. In this equation we have several variables. Ck is basically representing the spectral component. Which spectral component is this? If k is equal to 0 then it becomes C0. If k is equal to 1 then it's the first C1, which is the first spectral component, and so on. And if you see at the right hand side of this equation we have 1 over n. Here n is the time domain periodicity, that the time domain samples are periodic after n number of samples. And we have summation sign x of n, which is the original signal values. Whatever the signal we have, we put the values in this equation. Then we have the basis function e raised to power minus iota 2 pi k over n into n. So here basically you can see we have three variables to encounter, which are, first one is capital N. You can see I am highlighting with the pointer. First one is the capital N. Second one is the small n, and third one is k. So basically these three are the variables which are present in this equation, and we have to deal with these three variables smartly to obtain the values of spectral components, which are C0, C1, C2 and so on. So in this proof what we are going to do, the statement is saying Ck is equal to Ck plus n. So we replace k by k plus n in the above equation. So after replacing, equation becomes like this. Here you can see k is present here. We have replaced it with k plus n, and k is here, so we have replaced it as well. So the equation become like this. Now we separate out the basis function. Here we have k plus n, and we can write k plus n as this term, and by expanding this term we can actually cancel this factor, which is n with n, so we get 1 here. So you can see that we have cancelled out the capital N, and the equation is now simplified. Now we are left with this basis function e raised to power minus iota 2 pi n. Now we have to deal it with this basis function smartly. We already know that e raised to power iota theta is equal to cos theta plus iota sin theta, or if we have e raised to power minus iota theta, then it must be equal to cos theta minus iota sin theta. So by using that relationship, we expand this basis function e raised to power minus iota theta is equal to cos theta minus iota sin theta. And we know the values of cos 2 pi n and sin 2 pi n. At any integer value of n, we will get cos 2 pi as 1 and sin 2 pi as 0. So we get 1 as the answer of this basis function. So putting this 1 in the above equation, and our equation become like this, and you can see that it is actually the ck where we have started. So this is the actual ck, and ck plus n is equal to ck, or in simpler terms we can actually prove the statement the spectrum is periodic after every n samples, where n represent the time domain periodicity, and we proved that statement mathematically. And you notice that how smartly we put the value of k plus n in the equation, and then we separate out the basis function. Then we deal with the basis function by using identity, and after putting the value obtained from that identity, we ended up with the result ck plus n is equal to ck, which is required from our side to prove. So this is the generic proof. We are going to learn the usage of this expression by using some numerical values, or by taking some arbitrary signal in the later slides. Now we are going to see the numerical aspect of discrete time Fourier series, and how we can actually implement the analysis equation on some numeric values. For example, we have a signal x of n which is already discretized, and the sample values after discretization are 1, 1, 0, 0. It means by looking at this signal, we can say that we have 4 sample values, and you can notice that one is already bold, or somewhere you can find that it may be bold, or it may be underlined, or it has some arrow beneath it. So all these 3 indication is representing that this is the first sample value, or the sample value where n is equal to 0, which means the center value, or where the signal is starting, or where the value of n stand 0. So at the right hand side of this arrow, values are like +1, +2 and +3, and the values at the left hand side of this arrow are -1, -2 and -3 and so on. So this arrow actually representing the value at n is equal to 0. So in this question it is asked to obtain the spectrum of this signal where n is equal to 4 samples. So it is explicitly clarified that this is a periodic signal and this signal is repeating after every 4 samples. So actually we can take only the unique samples which are the first 4 values which are already taken in this sequence 1 1 0 0. Already 4 samples are given. So if 8 samples were given and it is mentioned that n is equal to 4 samples, the signal is repeating, so we can get the result by taking only the 4 values. So we are actually supposed to obtain the knowledge of frequency components present in that sequence or the signal composed of that sequence. So first we have to observe that which technique we can apply on this signal. First we have to see the parameter, either this signal is continuous in nature or it is discrete. So we can easily comment that it is a discrete time signal because discrete samples are given or sequences given or expression is given in the form of x of n. So this signal is a discrete time signal. And the second parameter which we have to look for is its periodicity, whether it is a periodic signal or it is an aperiodic signal. And here it is explicitly mentioned that n is equal to 4 sample, and we know that n is representing the time domain periodicity, that this signal is periodic after every 4 sample. So by looking at these two parameters and judging these two parameters, we are now sure that we can apply DTFS, which is a discrete time Fourier series, to analyze this signal. And after applying DTFS, we come up with the result which will actually tell us the presence of frequency components or spectral components in that signal. So let's start with the solution of this question. As we have already analyzed that it can be solved with the help of analysis equation discrete time Fourier series, and the analysis equation is written on the slide. Here in this equation you can observe you have to deal with several variables while solving, which are capital N, small n and capital K. So you need to solve these variables and put the values of these variables very smartly, otherwise you will get stuck in the solution. So for your easiness, I have mentioned the proper order to solve these variables. Here you first need to put the value of capital N And remember, capital N is actually representing the time domain periodicity. And from where you will get the value of N? It will always be mentioned in the question, or you can extract it from the sequence values, that by after how much samples your signal is repeating itself. So by observing the repetition pattern of the sequence, you get to know the value of capital N. But here you can see that capital N is explicitly mentioned in the question as 4. So you first have to put the value of capital N in this equation. Then after putting the value of capital N, which is the time domain periodicity, you have to expand the summation sign, which means you have to vary the value of small n by 0 to n minus 1. It means you actually expand this equation or summation sign by putting the sample values instead of this xn. Actually, if xn is 0, x of 0, then you will put 1. If x of 1 is asked, then you will put 1 again. If x of 2, then you will put 0. And if x of 3 is there, then you will put x of 0 instead of x of 3. And you have to vary it till n minus 1. And here n is equal to 4. So you have to vary small n from 0 to 3 as far as this numerical is concerned. However, if n is anything, or n has some different value in any question, then you will vary the value of small n accordingly. Then at the third step, you have to vary the value of k, which means you will actually find the spectral component values, which is the first spectral component C0 or C1 or C2 and so on. And by how many variables you have to vary k? You have to vary k by 0 to n minus 1, and again n is 4, so you have to vary k from 0 to 3. So actually you will get 4 values in this question, because n is 4 here. So we will get 4 spectral component information after solving this numerical, which are C0, C1, C2 and C3. So proceed with the solution. As discussed, we first have to put value of capital N as 4, and we actually put the value of n here and here, so we will get this expression. Our next step is to expand this equation with small n, which vary from 0 to 3. So after expanding, our equation become like this. You can see 1 over 4 remains the same, x of 0, because n is varying from 0 to n minus 1, which is 0 to 3. So x of 0, x of 1, x of 2 and x of 3. And here also there is k. So when you put 0 in the equation, so here x of 0, and in the basis function you will also put 0 here. When you put n is equal to 1, then x of 1 and k equals to 1. Sorry, n equals to 1. Similarly, when you put n is equal to 2, so x of 2, and here you put n is equal to 2. and when you put the value of n is equal to 3, so x of 3, and basis function you have put also n is equal to 3. So actually in this step we replaced the value of n and expanded the summation sign from x of 0 to x of 3, and we also replace the value of n in the basis function from 0 to 3. So after expanding, your expression become like this. After this step, now we have to put the values of samples, which means whatever the sequence or sample values are provided in the question, we have to put that sample values in this expression. And we have provided with 4 values. For x of 0 we have provided with the value of 1. For x of 1 we have provided again with 1. For x of 2 0 was there. For x of 3 0 was there. So in this step we actually put the values of or actual values of the signal. So we will solve this expression further. As you already know that anything multiplied by 0 result in 0, so these last two terms will become 0. Now you have to deal with only these two terms. So simplifying further, as you know that e raised to power 0, which is equal to 1, so we have actually replaced e raised to power 0 by 1, and we have simplified the second term as well. Here we have 2 and 4, we cancel out and simplify, and the expression becomes like this, which is the generic expression of Ck for these sample values. Here you can notice we cannot simplify it further. So now we can put the values of k, and as we discussed, k will also vary from 0 to n minus 1, which means 0 to 3. So first we put value of k as 0. So after putting, Ck becomes C0, and in the basis function we also put k as 0. So the whole expression becomes e raised to power 0, and you already know that e raised to power 0 is, and as you all know that e raised to power 0 is 1, so 1 plus 1, which is actually 2 over 4. Further simplified, C0 is equal to half. So by this we actually get the value of C0, which is half. Now we are going to vary the k as 1. So if we put the value of k as 1 in the generic expression or the simplified expression, we actually get with this expression, which is 1 over 4, 1 plus e raised to power minus iota pi by 2. So again we can simplify this e raised to power minus iota pi by 2 by using the relationship as shown in the slide. We all know that e raised to power iota theta is equal to cos theta plus iota sin theta, and here e raised to power minus iota theta is there, so we have used the negative sign with the sine term. So after solving this we actually get minus iota, because we know that cos pi by 2 is 0 and sin pi by 2 is 1. So here we get minus iota. So C1 is 1 over 4, 1 minus iota. Now putting k is equal to 2 to obtain the value of C2. So when we put the value of k as 2, the basis function becomes e raised to power minus iota pi by, or simply 2 cancelled with each other, we will get e raised to power minus iota pi. And again it can be expanded by using the identity cos theta minus iota sin theta, and we will get minus 1 here. So C2 will become 1 over 4, 1 minus 1, which is 0. So C2 is obtained as 0. So these are the knowledge of spectral components actually, C0, C1, C2. Now we are going to put k as 3, and when we put k as 3, the basis function will become e raised to power minus iota pi 3 pi by 2, and again by expanding the relationship or basis function by using the same identity, we actually get up with the result iota, and C3 is equal to 1 over 4 into 1 plus iota. So we will not further vary value of k, because we actually have to vary k from 0 to n minus 1, and n minus 1 is equal to 3 as far as this question is concerned. So we actually varied k by 0, 1, 2 and 3. So we will not vary it further, and we are actually ended up with our answer, which is the value of the spectral components, which are Ck. And here you can see the value of C0 is placed as half, the value of C1 is 1 over 4 into 1 minus iota, the value of C2 as 0, and the value of C3 as 1 over 4, 1 plus iota. And again it is very important that you have to mark the value of first spectral component, which is the same as the value of the first sample or the marked sample or the centered sample. If the sample was marked, if the sample 1 was marked as the centered element or the centered sample, which is in this question, then you have to actually mark the same value in the spectral component as the index value or the center value. So you already marked half as the centered value with the help of arrow sign. So we have alternate method to find C0, which is very easy. Actually you can find the C0 by using this expression or this formula also, which is summation x of n divided with the capital N. And by summation x of n, I mean to say all the sample values are added up and divided by capital N, which is the time domain periodicity. So we can actually add all the samples given in the signal, which are 1 plus 1 plus 0 plus 0, and divided with the time domain periodicity, which is 4. So we get up with the 1 over 2. So which is the same result we obtained with the x by using the standard expression. So for C0 only you can use this expression, or you can go with the standard formula. So both are equally valid. So there is no shortcut method to find any other spectral component values, which may be C1, C2 and C3. This formula is only applicable to the C0 value. So you can use this formula to find the value of C0. So actually we are ended up with our final answer, which is the spectral component information and its value. Hence we can do one thing with this result. We can actually divide our result into two components or two spectrum, which are the magnitude spectrum and the phase spectrum. So if we take the magnitude of these values, as you can see that iota is involved in this, so we are ended up with the magnitude spectrum by taking the mod of values. And if we want to find the angle, then we can find by using the identity or relationship. So we are actually ended up with the magnitude spectrum and phase spectrum information of this numerical.